Okay. So this particular equation that we have for the mixtures is quite universal that way. So what we had was mu A of the mixture. So we have a mixture of two gases at some temperature, at some pressure, okay, is, let's call this pressure total. Okay, this is the total pressure of these gases. Okay, and this would be less than or equal to mu A of pure at the same temperature and pressure. Okay, so here I don't need to write pressure total. We can just do with same pressure and temperature. Right? So it's always true, and you could actually derive this very straightforward. You could make a box over here, right? And let's say there's a permeable membrane which is permeable only to gas A, and let's have gas A on the right hand side and a mixture of gas A and B on the left hand side. Okay, and their partial pressures, let's say, are PA prime, PB prime, and on the right what we have is PA. Okay. So what will happen is that some of the gas molecules will cross from here and some of them would cross from here, right? And at equilibrium will be achieved when the Gibbs free energy of the left side is equal to the Gibbs free energy of the right side, or the chemical potentials are equal. So at that point of time, what I have to write, at equilibrium, the Gibbs free energy of species A in the mixture at the given temperature at a pressure, that is total pressure, that's partial pressure of A and partial pressure of B on the left side, would be equal to the Gibbs free energy of A on the right side, which is pure at temperature T and partial pressure of A. Yes. So what I can then use the Dalton's law on the right hand side, right? And the partial pressure of A would be nothing but, see, the partial pressures on the left and the right should be equal. Only then it will be in equilibrium. So the partial pressure of A would be equal to the partial pressure of A prime at equilibrium. Yes? No. See, individually all of them should be equal, right? Of species A, right? Of species B also, but there is nothing on the right. Would be 0. So each and every species, it has to be equal.
So potential of the gas is 0 also left hand side.
Would be naturally. Yes. We'll worry about that later. But let me write this as equal to mu A of the pure substance at temperature, and then use Dalton's law, right? XA times the total pressure. Yes. And this one I can then write it in terms of mu A defined at some standard pressure plus RT log of XA. If I assume these are ideal gases, is equal to mu A defined at the standard pressure of 1 bar at whatever temperature plus RT log of XA.
So we cannot write this for Q because there would be no equilibrium for
Right. There's no equilibrium. I mean, he does not go, so there's no problem. There's nothing on the right. Which is nothing but mu A naught T plus RT log PT plus RT log of XA, right? And this fellow, I already recognize this is the chemical potential of the pure substance, is equal to chemical potential of pure substance at temperature T dt. And on the left hand side I had chemical potential of the mixture at temperature T Pt plus here I have RT log of XA. Now since XA is always less than 1, I know that the chemical potential of the mixture is always less than the chemical potential of the pure substance. And this is important. I mean, I've already told you this in case of a liquid solution, but it holds true in general. Okay. And this is important in establishing the criteria for equilibrium when we see how a reaction proceeds. So then let me tell you exactly. The thing is that if you want to study some particular reaction, you would like to see at what temperature, at what pressure you want to carry out this reaction, and all these things are dictated by both thermodynamics and kinetics. Okay, so kinetics we will not worry about for the moment, but thermodynamically at least it should be a feasible process. It should be a spontaneous process. And one of the reactions that's very interesting is the Haber's process, making ammonia from nitrogen and hydrogen. And the thing is, it's very important because today in the world it consumes about 1% of the total power that is generated to make ammonia. Okay. So you can imagine how important this reaction has been. Sometime in the early 1900s, this was discovered by Haber, who managed to make, I think, 125 milliliter per hour or per day. And then Bosch, he managed to, chemical engineer, right? He managed to upscale the reaction. And from there on, they managed to get some good ammonia. And it was very important because this was, I think, around 1910s where they discovered ammonia, and 1910 or 1913 or something of that sort. This was the period of the First World War. And before that, ammonia was made using sodium nitrite or sodium nitrate, one of those. So, which was available only in Chile. And Chile was under British occupation. So, I mean, Germany had no control over saltpeter. They could not get in. And if they did not, ammonia is the one that is used to make all the explosives too. I mean, other than fertilizers. Okay. So if they did not have this means of making ammonia, Germany would not have lasted in the war also till 1918. Right? So it's a very important process. I mean, this is the birth of the chemical industry actually, making ammonia. So you can imagine how important it is. All the big giants that we hear of, BASF, I think it was BASF who finally took this process. Bosch, the the person named Bosch. Both Haber and Bosch were awarded the Nobel Prize. So all the major chemical companies actually came after the Haber process was invented, and most of the companies that you hear of today have German origins. BASF, Merck, Bayer, all of them. Anyway, so that apart, the process is like nitrogen plus hydrogen giving you ammonia, right? At some, so all of them are gases, right? At some temperature, some pressure. Let's just balance it for the sake of it. And now the thing is that it took a lot of time. I mean, you have enough nitrogen, but somehow people were mixing them, heating them up. But it really took a lot of time and a good deep understanding of the process that is going behind in order to actually carry out this reaction. And we'll see this equilibrium process, and then you'll get to know what exactly was required in order to overcome the problem associated with this particular reaction. Okay, so quickly we'll go through the equilibrium. So let's say that in general we have A plus B going to C plus D. They're all gases. So all gases at some temperature and pressure. So we'll carry out the reaction at some particular temperature and pressure. So we have to worry about delta G. Okay. So right, and let's say we have, let's introduce stoichiometry as well. A moles of A, B moles of B, small c moles of capital C, D moles of D. Let me just put this tail so that we can distinguish between small and capital D. So that's the process happening, and I want to see whether this process is spontaneous or not, right? So the first thing that I'll worry about is to see what is the change in the Gibbs free energy, and let's plot this. Let's say this is our delta G, and that's kind of an extent of reaction. Let's say we have this is all reactants, this is all products. Okay, and this is some coordinate which defines the extent of the reaction. Okay, so what we have then is it's gone. Okay. So what we have then is, in order that it be spontaneous, what I definitely need is that the total delta G of the reactants should be higher than the total delta G of the products. And I'll do that, I'll plot that over here. Let's say this is delta G of the reactants, and let's say this is the delta G of products. Okay, so I would start from here and go something like that. That would be my course of reaction, right? But over here, there's something that I'm missing out. And the thing that I'm missing out is, what I'm considering essentially over here is, okay, A plus B going to C plus D. The kind of picture that I'm taking over here is that these all A, B, C, D, they are in separate compartments, right? This is the kind of picture that I'm thinking of at the moment. Because then I would define the Gibbs free energy of the reactant A plus the Gibbs free energy of reactant B, add it up, that's the line I get over there, the green one. Gibbs free energy of reactant C plus Gibbs free energy of reactant D, add it up and get it over there. But this is not true, because just now you learned that the chemical potential of a mixture is less. Of species A in the mixture would be less, species B in the mixture would be less compared to the pure one. And if that is true, then what I should be plotting is not here but something over here. Right? And if that is true, this entire thing line would also come down. But that would depend on the mole fraction of each component. Yes? And we'll see how it exactly comes down. We'll have a look at that. Okay? I'll not draw it for the moment. I'll do a bit of maths and then we'll see how it actually comes down.
So how can we actually feel that this substance then pure substance is converted into a mixture?
Yes?
The chemical potential of that substance in a mixture gets increased.
Decreased.
So according to the formula we derived, mu chemical potential of A in the mixture is equal to pure chemical potential of A
Yes.
plus the RT and NX.
Yes.
Then chemical potential of A in the mixture is
Less. XA is less than 1.
so how does it decrease? How can you feel it?
Okay?
Other than mathematical explanation for it.
Other than mathematical explanation, how can I? Physical explanation is just that, for example, in the case that I took A plus B, I know that the pressures should be equal, right? That's more physical. From there I go on to derive delta G, or the chemical potential, right? So physically I'll have to either measure pressure, volumes, temperatures only. Okay, so over here what I'm talking of is actually A plus B going to, well, I don't know where exactly I'll land up, so let me just write everything over there. So I don't know if I'll land up over here or somewhere in between. So if I land up at the end, then of course A and B are 0 over there. Okay. So now what we have to worry about is where exactly I'm going to end. And for that, I see what is the Gibbs free energy at any point. So let's say my reaction has proceeded to a certain point over here, okay, and I want to see how further will it proceed. So by changing the reaction coordinate by an amount epsilon, a small amount, I want to see what's the change in delta G, right? So I want to see what is the change in delta G in this direction if I change it by a small amount. Okay. And what would happen is, yes, warning we can get rid of. What we would have then would be, we would need to calculate the Gibbs free energy at this point and the Gibbs free energy at the starting point. So at the starting point, let's say I have my partial pressures defined over here. So I have PA, PB, PC, PD, some partial pressures of the gas, of each and every gas over there. And what I want now is to define the Gibbs free energy at that starting point. Okay. That Gibbs free energy is nothing but A times mu A plus B times mu B plus C times mu C plus D times mu D, right, to start with. And then I increase the amount of C and D by some amount epsilon, right. So epsilon is kind of a reaction parameter. Okay, so it's like if I increase the amount of C and D, it would be epsilon times C and epsilon times D. So G at the second point, so at first point, at the second point, let's say, is A minus epsilon A times mu A plus B minus epsilon B times mu B plus C minus epsilon C times mu C plus D minus epsilon D times thanks, plus this is adding mu D. And then I need to see what is the delta G when I change the reaction by this amount epsilon. So that is G final minus G initial which comes out to be epsilon times C times mu C plus D times mu D minus A times mu A plus B times mu B. Yes? Amounts present at that point, right? Yeah, they cannot be at all. Otherwise my epsilon would be too large. I want a very small change. So now remember, all these chemical potentials are at the given pressure and temperature. Okay? And now I can write each of them as being present in the mixture, right? So I can write this as chemical potential of pure C plus RT log of pressure of C. Or I mean, I already know this, del G by del P at constant T, right? I know the expression from here that mu is equal to mu naught plus RT log of P, right? From here we had derived this expression, mu at any temperature T. So P by P naught, whatever, right? So I can put this expression over here, and yes, so it would be epsilon delta G of epsilon would be equal to epsilon times C of mu C at the standard state, that is 1 bar, plus RT log PC, right, plus D of mu d at the standard state plus RT log PD minus A mu A naught plus B mu B naught, this thing, plus I'll write the entire thing together, RT log PC, and since it's multiplied by C, it would be PC to the power C, PD to the power D by PA to the power A, PB to the power B. Huh? So, oh sorry, I closed the bracket just before that. I can put it there. Okay. Now I say that I actually change this for a unit epsilon, right? And then I see that delta G is nothing but is equal to something over here. Let me just encircle this. This is nothing but the delta G of the reaction, what we calculated initially without mixing. Huh? So this is at the standard state. Yes. So this is the delta G of reaction without mixing. This is what you normally calculate when you do all your calorimetric studies. So what we write over here then, this is equal to delta G of reaction, okay, plus RT log. Let me write this fellow is equal to Q, okay, plus RT log Q. Okay, we call this as the reaction quotient. Right. Now what do I want over here is that at equilibrium, yes, at equilibrium delta G is 0, right? Which means that delta G reaction at the standard state would be equal to minus of RT log Q, equilibrium. So what I get is at equilibrium delta G reaction is equal to minus RT log Q equilibrium. Yes. Now Q equilibrium is pressure of C times pressure of D raised to power C raised to power D divided by pressure of A, pressure of B raised to power D, right? So if at equilibrium any of these species A, B, C, D is present, then that means my equilibrium is not the reaction and not the product. Right? It is somewhere in between. Yes? That is the point where the delta G would be equal to 0. Right? So let me go back to the figure which we were making over here. And let me get rid of this for the moment. So delta G equals 0 means the slope should be 0, right? The slope should not change, which means this is something of this sort. Maybe I'll try something better. That's correct. Yes, but only thing is, why it's going down is obvious. The reason is mixing. Yes, it's all because of mixing, and these mixings are at different proportions throughout the reaction. Okay, I could have told you that, but now after knowing the math, you can easily realize that it's actually because of mixing. It's because of that component RT log PA that comes in, that everything goes down. Essentially, again, going back to the fact that it's the entropy of mixing that brings this curve down compared to what you would have had if you had individual things not mixed together but just reactive. So that's it. This is your equilibrium position over here. And if I do a reaction starting with A and B, I'll always end up over here. And you can imagine that if I try doing a reaction with anything, there will be always some entropy of mixing, which means I can never go to the completion of the reaction. I can go very close, yes, but never to the completion of the reaction. Right? Okay. So this, now remember this Q equilibrium, the reaction quotient at equilibrium. The reaction quotient is defined for all the points on the reaction, but this one is special, it's at equilibrium, and this has a name, it's called Kp, right? Kp. So what we can write is delta G reaction is equal to minus RT log Kp, or Kp is equal to e to the power minus delta G naught reaction by RT. This is how you relate. This is the equilibrium constant, right? Pressure of D raised to D, pressure of A raised to A, pressure of B raised to B. One quick question. What are the units of Kp? Okay, how many of you go for unitless? That's kind of quick. How many of you go for depends on the number of moles? There were more voices, huh? The confidence level is low. Okay, so the majority of the class seems to be right. It's unitless. It's diamond. It's actually, although I'm not writing over here, but it's always Pc upon P5, phi or P naught, whatever, right? The standard pressure of 1 bar which you are using generally. So it all gets cancelled. All the equilibrium constants, no matter what anybody tells you, are unitless. Okay. Let me write this in terms of mole fractions. Okay. So if I say Pc, then Pc would be equal to P total into Xc, right? So that means P total to the power C times Xc to the power C, which is equal to P total to the power C into Xc to the power C, P total to the power D into Xd to the power D. I can add it over there. Yes? P total to the power A into Xa to the power A, I can subtract this, I can subtract B. So that's like P total is the total pressure, right? I can just write P. That's the pressure of the entire system. That's what we are talking of. So this is a delta stoichiometric, let's say delta nu, okay, times, let me define that as kx. So this fellow is kx. Based on the mole fraction, this is the equilibrium constant. What will be the units of kx now? It's again unitless, right? Because although this p to the power delta nu is there, but it is divided by standard pressure to the power delta nu automatically, as I have taken it out from the expression. No units. But remember, Kp does not have a dependence on pressure on the total, but Kx would have a dependence on pressure. Yes. This. So Kp, first thing, Kp does not have a dependence on pressure, and Kx is equal to Kp times p to the power minus delta nu. When I do an example, then you'll see that you can't say the other way around, because yeah, sometimes it does look like that you can say the other way around too. Okay, so let's quickly do one example over here, and we'll come across one of the principles which you already know, but just make that belief stronger. N2O4 gas in equilibrium with 2 moles of NO2 gas. Okay, to start with, I have n number of moles here, nothing over here, and at equilibrium I have n minus x number of moles of N2O4 and 2x moles of NO2, right? And then let's calculate Kp from here. So the mole fractions are like n minus x over n plus x, right? And 2x over n plus x, and the value for Kp would be the partial pressure of NO2 square divided by the partial pressure of N2O4. Yes, that's P total square by P, that is P delta nu would be just P times x of NO2 by x of N2O4, right, which comes out to be 2x square 4x square P times 4x square by n minus x n square minus x square, right? Let's define something. I mean, I need to get to the the point where I can see what is the extent of reaction happening. So let's define something. The extent of reaction, and let's define that as the amount of NO2 formed divided by the amount of N2O4 that we started with. That would be good to define something like the extent of reaction. Okay, so what I get for Kp then is equal to pressure into 4 alpha square over 1 minus I just want the extent of reaction. Yeah. I could have taken 2x's, doesn't matter. But you know why I actually took x? Because at the end I want n by n. So the extent of reaction I want is 1 at the end. So that's why I divided by the stoichiometry. Okay, if I do some juggling around, then what I get is alpha is equal to 1 plus 4p by kp to the power minus half. Okay. What happens? I mean, you can do that algebra and you get back the same thing. What happens, essentially, what happens if I increase pressure? What happens to alpha? Huh? If I increase pressure? No, this is 1 over 1 plus 4p. So if I increase pressure, then the denominator increases, alpha decreases. Right? That means if I increase pressure, the extent of reaction goes down. Yes? If on the other hand I decrease pressure, the extent of reaction, that means the reaction goes towards the product side. What we have over here is that we have more gas on the product side. If I increase pressure, the equilibrium is driven to the left. If I decrease pressure, the equilibrium is driven to the right. Which means if I am increasing pressure, the reaction is behaving so that it tries to minimize the number of moles or resists that pressure. And this is a principle that everybody knows, right? Le Chatelier's principle. Right? We could do more examples. Now, we're done with pressure. Let's see the effect of temperature on the change in the Gibbs free energy. Right? So what we had over here was log of k, which is a function of temperature, was equal to minus delta G by RT. Yes, this is where we had left and before the example. So d log k by dt would be equal to d of minus delta G naught by RT by dt, which I'll have to do it by parts. And I have to worry about d delta G not by RT by dt, right? We fix the pressure, right? The pressure is constant, so we want to see what is we fix the pressure, right? We're doing this reaction at a constant pressure, and now we want to see what is the variation of delta G as a function of temperature. So let's go back to the thermodynamic equation of state. What we are actually interested is in d delta G naught by del T at a fixed pressure, right? I want to, essentially my fixed pressure is also defined, it's 1 bar, minus delta H would come out to be minus delta H. It's defined to be 1 bar because this is it, delta G naught is what I'm saying. So this fixed pressure is actually nothing but 1 bar. Yeah, so we go back to the fundamental equations of the thermodynamic equations, the fundamental ones, and dg is equal to minus v dp, no, plus v dp minus s dt. So for the initial one I'll get minus s initial, for the final one I'll get minus s final, and take a delta G, so I'll get a delta S minus delta S for the standard state, which is also a function of temperature. So then I can write the above expression, delta G naught I can write as delta H minus T delta S. So what I get is delta H naught minus T delta S naught by RT square minus 1 by RT into delta S naught minus minus, I'll just make it a plus. We can get rid of this too. And then what I have is d log k by dt is nothing but the enthalpy, the standard enthalpy of the reaction divided by RT square. So that's what you already know. I think people already know the Van Hoff equation. I could integrate this equation and get straight away log of k2 minus log of k1 is equal to integral from t1 to t2 delta h by RT square dt. I can assume delta h to be constant over a temperature range. If I don't assume, then I can use delta h at some temperature is equal to delta h at temperature T2 is equal to delta h at temperature T1 plus delta Cp times T2 minus T1. I can use that, but for most, for most of the times I don't need to, since I can assume delta h to be constant. And if I assume delta h to be constant, then what I get is log of k2 or k at T2, if you want to call it that way, is equal to log of k1 plus minus plus, ठीक है, 1 by yeah, there will be a minus sign, right? So okay, let's take care of the minus sign here. Okay, so that's how the Gibbs free energy or the equilibrium constant varies as a function of temperature. Right. So if let's go back to Le Chatelier's for temperature. If this fellow is exothermic, if it's negative, and I increase the temperature, that is T2 is larger than T1. So that means the whole thing comes out to be negative, right? Which means K2 would be smaller. That means if for an exothermic reaction which is already giving out heat, I raise the temperature, the reaction will move in the backward direction. If I do the opposite, if I lower the temperature, the reaction will move in the forward direction. If it's endothermic and I increase the temperature, the reaction will move in the forward direction. So that's Le Chatelier's principle for temperature, right? Now, after having studied so much about equilibrium, let's come back to the original problem that we posed, the Haber's problem. Okay. That was the most worrying of all. Now, let me give you the data. For this reaction, nitrogen gas at whatever temperature pressure you prefer, hydrogen giving you ammonia gas at that temperature and pressure, the delta H naught of the reaction at room temperature is minus 46.21 kilojoule per mole, and the delta G of reaction is minus 16.74 kilojoule per mole. Okay. So the reaction is spontaneous. I mean, delta G is negative, right? Let's calculate Kp for this. The equilibrium constant Kp. That would be the pressure of ammonia divided by pressure of hydrogen to the power 3 by 2, pressure of nitrogen to the power half. Yes. In terms of mole fractions, if I write, then here I have 1, here I have 3, 1, 2, minus 1, right? So P to the power minus 1 mole fraction of ammonia by mole fraction of hydrogen to the power 3 by 2 mole fraction of nitrogen to the power half. Yes, which is nothing but e to the power minus delta G naught by RT. So I can just calculate this. This comes out to be, I mean, in the absence of calculators, I'll just I don't expect you to carry calculators to the class, but definitely to the exam. So 860, right? So we have a lot of ammonia over there. Yes. So in principle, the reaction is spontaneous. It should be feasible at room temperature. What's stopping it is kinetics. Okay. There's huge activation barrier. The NN triple bond is a very stable bond, right? So it does not form. So what to do? Raise the temperature, right? But if I look at the value of delta H, it's negative. Right? If I raise the temperature for an exothermic reaction, it will go towards reverse side. So what do I do? And that is right. And that is the whole problem now. Catalyst is another thing which can lower the activation energy, but there are some more things which need to be done. Yeah. If I definitely have to raise the temperature. So let's see what happens if I actually raise the temperature. Let's raise the temperature to 800 Kelvin. And this gives me a value of Kp equals to 0.007. Okay. That means if I raise the temperature, the reaction is unfeasible. A very little amount of product is going to come out. That we have discussed. Right. What's interesting to note is that Kx is equal to P times Kp. Kp does not have a pressure dependence again, but Kx does. And from this example, you will really see how it does. So if I am doing at 1 bar, then Kx is equal to Kp. Okay. But if I increase the pressure now, I'll have more number of moles of ammonia in the reaction mixture. The mole fraction of ammonia will increase because Kx would be, let's say, increase it to 100 bar. So 1 bar Kx is the same, 100 bars Kx equals 0.7, right? So, which of course looks more promising. Now what I can do is, if I want that the mole fraction of ammonia be large, practically what I have to do is, as soon as it's formed, remove ammonia from there. Yes, and then it will be large. Now, this is what, oh, got it. So, this is what the ingenuity of Haber was. Well, I think the Haber process is carried out at 200 bars. That's a huge pressure. And I think he was at Karlsruhe, one of the universities in Germany. And if you go to that university, you can actually see this. The first reaction chamber made of steel. It is like a museum kind of thing, housed outside the university. I've just seen the photo. Okay. So what he did was to do the reaction at an elevated pressure, so that it can be carried out. The temperature, of course, he added some catalyst as well. But in fact, the very interesting thing is that maybe I'll tell you that in the kinetics part, but Gerhard Ertel yeah, that's how it's pronounced. So he was a Nobel Prize recipient in 2007, mainly for surface chemistry. But he elucidated the mechanism of formation of ammonia. It's essentially nitrogen and hydrogen which go and get absorbed on the catalyst, break up into atoms, and the atoms combine together. Then we'll do it in kinetics as an example. So Howard got it for making ammonia. He didn't get it for making for discovering the reaction mechanism of ammonia, but for lots of other studies. but he was the one who discovered the reaction mechanism of formation of ammonia. Sorry? To cross the activation barrier. So that's one thing. I mean, that's not covered in thermodynamics, right? Activation is a separate topic. Okay. So quickly, two things which I want to tell you apart from what we have done. One is, yeah, this is fine, this is clear. Okay. In solutions, so we've seen gases, mixtures of gases. In solutions, what you normally do is that the chemical potential of a substance A for a given temperature, pressure, right? Then you don't write mixture or pure. What you write is concentration of A is equal to mu A at the standard state at that temperature, pressure, plus RT log concentration of A. Now this concentration of A could be molarity, molality, right? Whatever units you prefer, it's fine. Of course, implicit over here is the standard concentration. Now, anything that is an argument of a log is dimensionless. Right? And likewise, if I do the complete analysis again as we did in the case of gases, instead of Kp, what I have a K equilibrium or K whatever you write, which would be the concentration of C times C, concentration of D times D, concentration of A times A, concentration of B times B. Okay. In case of gases, what we had over there was the standard condition was 1 bar. In case of solutions, it's a bit more tricky because it really depends on the solution. It could be some standard pH, it could be some salt concentration, it could be anything. It could be a lot of factors included over there. But let's assume that somebody has defined what the standard is. Okay. So you don't need to worry about that. And the last thing which I wanted to tell you is that if things are not mixing together, right, then their chemical potential in the mixture is as good as their pure chemical potential. What I mean to say is that if we have a solid, a liquid, and some gases, the gases mix together. The solid and liquid do not mix with each other, nor do they mix with the gases. If we have such a state, then it's the chemical potential of the solid in the mixture is equal to chemical potential of the solid as it would be in the pure form, right? The chemical potential of the liquid in the mixture would be the chemical potential of the liquid in the pure form. But in case of gases, of course, we would have the chemical potential of the gas in the mixture would be equal to chemical potential of the gas in the pure form plus RT log PA or RT log PB or so on. So just to complete that, what I'll have is delta G would be equal to, let's say, A plus B. Okay. Let's say A plus B is again going to C plus D, and out of these B is a gas over here and D is a gas over here. This is a liquid, that's a solid. Okay, so like the same analysis that we had done, C mu C naught plus D mu D naught minus so A, B, C and D times minus A of mu A naught minus B of mu B naught plus RT, and in the reaction quotient what we'll have is only the pressure of log only the pressure of the products in the gaseous phase to the stoichiometry divided by product in the reactants, that is B, pressure of the reactant, sorry, to the power B, right? Just 1 minute. So that's your delta G naught for the reaction plus RT log Q equilibrium or KP or whatever you wish to call it. This is fine? Ah.
So where can we use RT current X of X common Excel? You is also for the minimum plus RT in Excel.
Just see over there. What we are using over here is just the change. Okay, go back to that. That is in a mixture. This is for the pure. What I have done was the pure substance, the chemical potential of. Let me go back. Okay. G1 is chemical potential of A plus chemical potential of B plus C plus D. Right? I've just used the fact that I can write the chemical potential of A as the chemical potential of A at a standard state plus RT log PA. The equation that you are telling is for the mixture. When it comes to mole fractions, it's always for the mixture. I've just written for the pure one, right? Yes. No, there's nothing mixed in the liquid. If there was something mixed in the liquid, yes, it will come. Right? I mean, I have shown you an example where the solid, the liquid do not mix with anything. The gases mix. If two liquids mix, of course we have the terms for those also. Right? I mean, I cannot have the pressures over there. Yes. I'll have to use the concentration terms.